The latest image of the interstellar object 3I/Atlas has generated a new wave of scientific curiosity and debate, not only because it is the third known object to enter our solar system from interstellar space, but also because the physical characteristics revealed in recent observations raise unexpected questions about its nature. The image, taken on November 5, 2025, by the Lowell Discovery Telescope in Arizona, captures 3I/Atlas at a distance of 1.38 astronomical units from the Sun and 2.23 astronomical units from Earth. Despite being relatively close in astronomical terms, the object appears in the telescope image as a compact, bright point of light, roughly comparable in size to the point spread function, PSF, that defines the instrument's resolution. This means that the object remains unresolved, too small in angular size to reveal structural details. Around this unresolved core sits a faint, diffuse glow resembling an atmosphere or a coma, a feature commonly associated with comets. Yet despite this faint haze, the image does not present clear evidence of a distinct cometary tail, which is usually the most recognizable characteristic of an active comet nearing perihelion. The image was taken in a green filter optimized to detect emission from diatomic carbon molecules, C2, a known tracer of cometary activity. Interestingly, the atmosphere-like glow around 3I/Atlas appears brightest in the bluest filter, suggesting the presence of gas species that fluoresce efficiently under sunlight at shorter wavelengths. Although this could be consistent with low-level cometary outgassing, the conspicuous absence of a dust tail remains puzzling, especially given the physical expectations for an object losing mass rapidly under solar heating. A typical comet near perihelion experiences intense sublimation as volatile ices evaporate from its surface. This process releases gas that drags dust grains outward, forming a bright, elongated tail pushed by solar radiation pressure and the solar wind. For 3I/Atlas, one would anticipate an even more dramatic display because of the non-gravitational acceleration reported by NASA's Jet Propulsion Laboratory. Non-gravitational acceleration in comets is usually interpreted as the result of asymmetric outgassing, where jets of sublimating material exert a small but measurable force on the nucleus. According to the momentum conservation arguments developed in the earlier analysis you referenced, the magnitude of the observed acceleration would imply that 3I/Atlas must have lost more than 13% of its total mass during perihelion passage if it were behaving like a normal, natural comet. Losing such a significant fraction of its mass should have produced a vast, noticeable coma filled with dust and gas, and this material should have spread outward to form a tail clearly pointing away from the Sun. The absence of such a tail raises the question of whether the assumed cometary mechanism is correct or whether something else is influencing the observed trajectory. One important caveat, however, concerns the geometry of observation. The image was taken when the object was only about 13 degrees away from the Sun in the sky. When a comet's tail points directly away from the Sun, an observer positioned nearly along the same line of sight may see the tail foreshortened, or even completely hidden, because it is oriented nearly head-on. This viewing angle could make a large tail appear deceptively compact, potentially blending into the unresolved bright core and faint surrounding coma. Still, geometric explanations alone may not fully account for what is observed. For one thing, this nearly head-on perspective was similar to the one experienced by the Hubble Space Telescope when it imaged 3I/Atlas on July 21, 2025. At that time, Hubble captured an anti-tail feature, material extending in the sunward direction, while observing at a comparable small angle of 10 degrees. This anti-tail appeared as a noticeable elongation of the object by a factor of 2 along the direction toward the Sun. Even though anti-tails arise from a combination of dust particle size distribution, orbital geometry, and projection effects, the fact that Hubble was able to clearly detect such a structure at a very similar viewing angle makes the absence of any analogous elongation in the new Lowell image rather surprising. This discrepancy leads to several possible interpretations. One is that 3I/Atlas may have exhausted or significantly reduced its volatile content during the perihelion passage, leaving little material to produce a visible tail at this stage. Another possibility is that the non-gravitational acceleration reported earlier may not be solely due to outgassing. In other words, either the physical mechanisms driving acceleration have changed since perihelion, or the forces originally inferred may need to be reconsidered. It is also conceivable that dust production occurred, but the particle sizes were unusually large, causing them to remain close to the nucleus instead of forming an extended tail. Alternatively, extremely fine dust might be present but spread diffusely, below the surface brightness threshold of the current observations. Each scenario carries its own implications for the composition, structure, and origin of 3I/Atlas, and distinguishing among them will require new data from a wider range of viewing angles and wavelengths. Fortunately, the coming weeks offer exactly that opportunity. As the object continues to move along its trajectory after perihelion, its angular separation from the Sun in the sky will increase from the current 13 degrees to several tens of degrees. This widening angle will allow telescopes on Earth to observe the object against a darker sky background and from a perspective where any tail directed away from the Sun would be seen more clearly in projection. If a dust tail exists, it should become unmistakable once the geometry becomes favorable. Likewise, if no tail emerges even under these improved conditions, the case for an unconventional explanation, whether related to composition, structure, or other forces, will grow significantly stronger. Solar illumination at the distance of 1.38 astronomical units delivers approximately 770 watts of energy per square meter to the object surface, enough to heat and sublimate typical cometary ices. If such intense heating fails to produce standard cometary signatures, astronomers will need to consider whether the object is composed of unusually refractory material, exhibits surface sealing that prevents gas escape, or perhaps belongs to an altogether different class of interstellar bodies. In the meantime, the scientific community, both professional and amateur, awaits the results of follow-up imaging campaigns across multiple observatories worldwide. Large telescopes equipped with sensitive detectors, spectrographs, and polarimetric capabilities will examine whether gas emissions strengthen or fade, whether dust production initiates or remains absent, and whether the object's brightness profile evolves in ways consistent with or inconsistent with known cometary physics. Observations in ultraviolet, infrared, and radio wavelengths may reveal molecules that are not easily detected in visible light, while time series photometry could uncover rotational variations that might hint at jets, surface heterogeneity, or structural irregularities. Each dataset will contribute a crucial piece to the puzzle of understanding what drives the behavior of this interstellar visitor. The excitement around 3I/Atlas is amplified by the broader context of interstellar object research. Following the earlier discoveries of 1I/Oumuamua and 2I/Borisov, the appearance of a third interstellar object provides an important opportunity to compare and contrast physical behaviors across objects formed around other stars. Borisov behaved very much like a conventional comet, complete with abundant dust and gas emission, whereas Oumuamua lacked a detectable coma and exhibited a peculiar acceleration that remains unexplained. If 3I/Atlas also deviates from standard cometary expectations, we may be witnessing a pattern in which interstellar objects display a wider diversity of compositions and behaviors than previously assumed. Such diversity has profound implications for theories of planet formation, the distribution of volatile materials in exoplanetary systems, and the processes that eject these objects into interstellar space. As scientists work to interpret the latest image and prepare for future observations, public interest in 3I/Atlas continues to rise. The 5 new letters mentioned as arriving in your inbox today reflect the fascination that interstellar objects inspire, not only among astrophysicists, but also among everyday people who are captivated by the idea of material from other star systems entering our cosmic neighborhood. These letters likely include questions, hypotheses, personal reflections, and reactions to the evolving story of this mysterious object. The fact that so many individuals are eager to engage with the science highlights how interstellar discoveries resonate with deep human curiosity about the unknown. Each new image, measurement, or theoretical analysis adds another layer to the narrative of exploration and discovery that connects scientists and the public in a shared sense of wonder. In the days and weeks ahead, the growing separation angle from the Sun will unlock the observational clarity needed to reach a more definitive verdict about whether 3I/Atlas possesses a cometary tail, or whether its behavior points toward a more exotic or unconventional nature. Until then, the scientific community remains alert, instruments are being readied, and the world waits to see what new insights this interstellar traveler will reveal.